All right.
Welcome to The Explainer. Today, we're diving deep into one of the most powerful forces in the entire universe. It's the strong nuclear force. You know, the cosmic glue that literally holds the core of every atom together. And we're going to explore a really radical new model based on a paper by physicist Dmitriy Plotnikov that doesn't just challenge a Nobel Prize-winning theory, it might just change how we think about reality itself. Let's get into it.
So, Plotnikov kicks off his paper with this quote, which is honestly the perfect way to set the mood. Because we're not just talking about tiny little particles here. We are pushing right up against the edges of what we think is real. We're about to ask some pretty huge questions about infinity, about energy, and maybe even the fabric of the universe itself.
So here's our game plan. We're going to start with the puzzle that's been around for ages, the atomic nucleus. Then we'll look at why the current explanation has some serious cracks in it. From there, we'll build up this new theory step by step, starting with rethinking what a particle even is, figuring out how they connect, and then we'll get to the really mind-bending stuff about space and time.
Okay, let's start with the absolute basics. You look inside an atom's nucleus, and you've got all these protons, right? They're all positively charged, crammed into this tiny space. Basic physics says they should repel each other and fly apart with an incredible amount of force. So, what's stopping them? What invisible superpower is holding it all together?
Well, the classic answer, the one that won Dr. Hideki Yukawa a Nobel Prize back in '49, is that a proton and a neutron are basically playing a game of hot potato. They're constantly tossing this little particle, a pi meson, back and forth. And in this exchange, the proton supposedly hands over its positive charge, becoming a neutron, while the neutron becomes a proton. And this constant swapping, that is the strong nuclear force. For decades, this has been the textbook answer.
But here's the thing. When you really scrutinize that model, when you hold it up to what we now know about quantum mechanics, some pretty big cracks start to show. The official story, it turns out, doesn't quite add up.
In fact, you run into three huge contradictions with the fundamental laws of quantum physics. First, a neutron is actually heavier than a proton, so how can a lighter particle just give mass to a heavier one? That breaks the rules. Second, quantum mechanics tells us that charge isn't some jacket you can take on and off. It's a fundamental, built-in property. It's part of the particle's identity. And third, and this one is the real showstopper, for any two particles to interact and exchange energy, they have to be coherent. They have to be fundamentally the same. A proton and a neutron, well, they're not.
This leaves us in a pretty tough spot. I mean, either the model is wrong, or some of the basic rules of quantum mechanics are wrong. Plotnikovich is betting the model is the problem. So the question is, how do you fix it? How do you solve this puzzle?
The solution starts with a pretty radical first step. You have to completely change how you think about what a proton even is. So forget that picture of a simple, single little dot. The reality in this new model is way more interesting.
Plotnikov proposes that a single particle, like a proton, isn't just one thing. It's actually a system of two distinct but identical or coherent quantum states. You can call them P1 and P2. They exist at the same time, they're identical to each other, but they each have their own spin. This is the cornerstone of the whole theory. A single particle is really a dynamic little system.
Okay, so if protons and neutrons are both these two-state systems, how does that help? They're still different particles. The real breakthrough isn't in how they interact directly. It's in how their states can be combined to create something new.
Here's the genius move. The interaction doesn't happen between the proton and the neutron at all. Instead, you take one state from the proton, P1, and one state from the neutron, N1, and you combine them. This creates a totally new point in space. Let's call it B1. Then you take the two leftover states, P2 and N2, and you create a second point, B2. Now here's the magic trick. Because of the way these new points, B1 and B2 are made, they are perfectly coherent. They're identical to each other. And now they have a way to interact.
So we've built our two coherent points. We've set the stage. So what happens between them? Well, what happens next is the strong nuclear force, according to this new model.
Okay, so just picture it. Point B1 starts out with a bit too much energy. It's in a high energy state, E1, which makes it unstable. It wants to get rid of that extra energy. So what does it do? It fires a little packet of energy over to point B2, which is just chilling at a lower energy state, E2. But now, of course, the roles have flipped.
Point B2 just caught that energy, so it's now in the high energy, unstable state. So what does it do? It sends the energy right back to B1. And this back and forth, this constant, continuous, oscillating exchange of pure energy, that is the force. It's not a particle being swapped, it's pure energy playing catch between these two specially made points.
And this isn't just a random exchange either. The model gets incredibly specific. It predicts that this force is only super strong at very particular discrete distances. And at other specific distances, the force just disappears. It basically creates these invisible zones of attraction, which might just explain the really strange, quantized nature of the subatomic world.
But hold on, it gets even wilder. The energy bouncing between B1 and B2 actually creates more coherent points between them. And those new points start exchanging energy, creating even more points. This whole cascade is called amplitude resonance. And what it does is it focuses the entire interaction down to a single, infinitesimally small point. And at that single point of convergence, the distance between the interacting parts literally becomes zero. Let that sink in.
And that brings us to the most profound, maybe even shocking implication of this entire model. If at the moment of energy exchange, the very moment the force is happening, the distance between things collapses to nothing, well, that has some truly mind-bending consequences for how we see the universe.
So, let's just quickly pull it all together. What are the big takeaways? First, the strong force isn't about particles playing dress-up and swapping identities. It's about pure energy being exchanged between these specially constructed coherent points. Second, this exchange is instantaneous. Why? Because the distance collapses to zero. Which leads to the next point. At that single point of exchange, our familiar ideas of space and time, they just stop having any meaning. And finally, charge isn't something you can give away. It's a permanent, fundamental part of what a particle is.
And all of that leaves us with this one last massive question to chew on. If the fundamental forces that build our reality are all based on this instantaneous exchange of information, where distance literally collapses to zero, then what exactly are space and time? Are they real fundamental parts of the universe, or are they just emergent properties, illusions that our big, slow, macroscopic brains create to make sense of a reality that is infinitely weirder than we can imagine? That's a question that could change everything. Thanks for joining The Explainer.